Okay, so let's get on to business then. So I'm Dr. Hines. I'm the nuclear engineering department head here at the University of Tennessee. We didn't send this seminar outside of the department like we usually do, but we did put it on social media. So welcome. Today we're very lucky to have one of our own speak with us. Dr. Deborah Penchoff is a high-performance computing HPC scientist and global security fellow at the Howard H. Baker Jr. Center for Public Policy. Since 2018, she has been the director of the Scientific Fellows Program at the UTK Institute for Nuclear Security, where she leads an interdisciplinary team with the goal of finding solutions to challenges of relevance in national and global security, with a focus on nuclear and radiochemistry. She received her PhD in physical chemistry with an interdisciplinary graduate minor in computational sciences from the University of Tennessee in 2014. Her doctoral work focuses on HPC applications for the optimization and design of extracting agents for separations of lanthanides and actinides. Her research is focused on the development of computational protocols for evaluations of bonding, reactivity, and detection of rare earth elements, critical materials, and actinides and applications relative to the national security. So welcome, Dr. Penchoff.
Thank you. I'm very happy to be here and talk to you all, unfortunately virtually, but I'm sure we'll get there next time. Okay, so I am going to share my screen. Let's see. Let me see. Do you see it?
Not yet. Here it comes. Here it comes.
There it goes. Okay, great.
We got it. Yep.
All right. I don't know. Okay. Do you still see it?
Yes, we're all set.
Perfect.
It fills the whole screen.
Awesome. Perfect. All right. Well, so I'm going to talk to you about applying HPC to separations of rare earth elements and actinides. This is very related to work that I've experienced nuclear engineers do a lot, but somewhat it seems tangential. So hopefully today I give you a bit of an idea on where these things merge. I'm going to talk to you about the goal overall of the research we've been pursuing, what the REEs are and the actinides, why they matter, how we apply HPC specific to separations, why we need separation optimization, and what we can do with an interdisciplinary approach in computational radiochemistry. The ultimate goal of the research is to enable knowledge-based designs of separation agents, specifically to target REEs and actinides. In the short term, we want to develop computational protocols that allow us to still get some type of reasonable, efficient answer without waiting decades. And in the long term, we want to develop tools that can take advantage of the exascale capability that we're entering in the HPC world, that we are not there yet for REEs and actinides. We are there for many other things, but not for this, and I hope I can show you why. Throughout this process, also we need to understand the complexation process that undergoes the binding of REEs and actinides so we can understand two things. One, how to separate them more efficiently, and two, what makes this element act the way that they do and make critical materials so special. And I'll cover all these concepts in a minute. So we basically have three parts here. We have a high need on rare earth elements and actinides. We have a high need to have the material. We have a high need to have them purified. And we have that need, and one of the aspects that can address this is optimization of separations, because we do need the materials. I think most of you in this group today will agree we need the elements. I think we forget a bit how we get to separate them to have them pure in form. And I'm going to talk about a tool that we're implementing in HPC to try to optimize the separations. I know it's not super common to see HPC applied to radiochemical separations. As Dr. Hines said, I did my PhD with Dr. Schweitzer and Robert Harrison, and that's exactly where these green and purple bubbles connect. So hopefully I can give you a bit of my experience and how that developed into a new aspect of the HPC scientific computing field. So let's take a look first at REEs and actinides, the needs, and how they're critical materials in a lot of society today. So I'm going to try to cover, and feel free to ask me questions, why they're important, what they are, what the rarity in them is, the resources and challenges we have in supply, and solutions and alternatives. So why do they matter? Why do REEs matter? They're essential in the growth and health of the US economy. You use REEs every single day in most things that you do, from your cell phone to your computer, to communications that use satellites. Anything of these applications have REEs. Our defense depends enormously on it. So national security depends on it in multiple facets. For example, just a few examples: catalysis, petroleum refining, converters, pollution scrubbers, chemical processing, all need REEs. Metallurgy, hybrid vehicles, electric vehicles, computers, all our computers need REEs. Steel production, ceramics, protective eyewear, optical glass, night vision goggles for the military, magnets. Don't minimize when we say magnets. Magnets we need for any of our little motors that run anything from clean energy to the ability to have, smaller and fancier headphones and computers and cell phones that today are like a supercomputer of the past. A lot of this is linked to the magnets and the type of magnets that you can make with REEs. So electronics, satellites, clean energy, as I said, are critical. REEs are critical for those applications. Phosphors, your screen displays, the fancy monitors and images we can see today, light bulbs. And for you in particular, how do REEs fit your applications and your need? Well, they're fission products. Also, uranium and thorium are extracted from ores in the earth, and they can mix with REEs. So you have to remove the REEs if you want to have your uranium and thorium. Defense and military, and multiple applications that I've experienced nuclear engineering students work on, even during their graduate studies. Radiation monitoring, medical applications, radiotherapy, MRI, nuclear waste has them. So we need to separate these elements for multiple needs, right? On one hand, to get the material that we need to use for something, and other times to separate it from waste so we can deal with the waste. And it's the same process to separate them, just a different need. So what are they? I'm not going to bore you too much with chemistry. I know your feelings about this, but I just want to point very quickly. REEs is just a name that is given to 17 elements that include scandium, yttrium, and the lanthanide series, all the way from lanthanum through lutetium. So that's what we know as REEs, just a name to a group of elements. And one of the applications that these REEs are critical for is defense. In defense, we have guidance and control systems. They require compact and powerful permanent magnets. For this, you need neodymium, praseodymium, samarium, dysprosium, terbium. Those are just 5 names of 5 REEs. You need them to allow you to create functionality in the motors and actuators, for example, for Predator, unmanned aircrafts, cruise missiles. See how this crosses over with a lot of the nuclear engineering needs. In electronic warfare, for energy storage, capacitance, you have a whole array and combinations of REEs for its applications. For directed energy weapons, for example, the batteries, the nickel metal hydride batteries you need for these instruments, electromagnetic railguns. For targeting and weapon systems, you need to amplify the energy and resolution. You use yttrium, europium, terbium. All the targeting and weapons is done through this, specifically laser technology. All the laser technology we have today is highly dependent on REEs. And look at the military, using lasers. Look at the variety of things that are needed. Any targeting that needs a laser to come first, for laser weapons or otherwise, will need yttrium, europium, and terbium. For electric motors, we need compact, powerful magnets again. neodymium, praseodymium, samarium, dysprosium, terbium. You're going to get tired of me saying these names for a little bit today. All the motors need this. Aircrafts, communications, amplification for signals. I know I had some colleagues in my previous group from the Navy, and they would talk about this a lot. They need neodymium, yttrium, lanthanum, lutetium, europium, radar, sonar radiation, chemical detection. See, the applications are critical on using these elements. So how rare are they? So we know they matter, and they matter a lot. So are they rare? Do we have enough? Let me tell you a bit about that. How rare they are. They're really not rare. It's funny that the name that was given to these elements is rare earth elements. They're not rare. They're very abundant on the Earth's crust. The challenge is that the concentration where you find them in the Earth is very low. The rarest form is promethium, and that's because it's not naturally occurring, like most of the actinides, except for uranium and thorium. The two least abundant REEs are thorium and lutetium, and they still are 200 times more abundant than gold. So see, they're not that rare. The least rare, cerium, yttrium, lanthanum, and neodymium, are as abundant closely to nickel, tin, and chromium. You wouldn't say nickel and tin are rare, right? So they're really not rare or uncommon. They're just scattered across the Earth in small deposits, and this is where the trick comes in. They're very difficult to mine and difficult to separate because of the way they come out all clumped up together. So they're rare earth all over the globe, as you can see in this map from the US Geological Survey. So why are we concerned about these elements, and why it seems like we don't have enough? Well, we have a supply risk. This is called the Endangered Elements Periodic Table. And here I marked the REEs that we're talking about. So in green, you see an element that is abundant. In yellow, you see an element that has limited availability. Yellow-red is like a rising thread, and red is there's a serious threat in the next 100 years. Notice the elements marked in black. Almost all of them are yellow, red, or yellow-red. So most, if almost not all of REEs are in supply risk. So where are we with this? DOE has been very interested in this for a while, especially since 2010, and I'll show you why in a minute why this happened in 2010. They created what they call the criticality matrix. They evaluated the supply risk of chemical elements and the importance to clean energy, and they created this. So as you see, as you go to the right and up, that will be something that has a supply risk and is very important to clean energy. And they classify the elements as red critical, yellow near critical, green not critical. If you look at the top right, all 5 critical elements are REEs. And from the 4 near critical, 2 are REEs. So the vast majority of the critical and near critical elements we need for clean energy are REEs that are in somewhat short supply, as we saw in the previous chart. So let's take a look at global production. We saw there were many ores scattered all around the globe. So why is there a supply risk? Well, let's take a look. In the early 90s, the US, shown here in red, and China in black, the rest of the countries in blue. The US was the largest producer of REEs in the world. It keeps being the largest producer or amongst the largest producers through the early 90s. And then China started selling REEs cheaper than the US. The way China was able to do this was because, as I mentioned earlier, the separation is difficult. But one of the challenges is that parts of the separation are very toxic. The solvents that are effective for targeting selective binding, selective separation of REEs can be toxic to the environment. The US tightened the rules to do toxic processing, but China didn't. So look what happens as the 90s keep going up. The global production of REEs is largely done by China by a lot more than the US and the rest of the world. Look at the gap. So China produces so much and so much cheaper than the US that around, in the early 2000s, the US basically stopped mining, stopped producing REEs competitively. And this keeps going on until 2010. In 2010, China limited REE exports. This is when DOE got involved and created the criticality matrix, and they also created the critical materials house that you have. I think they're led by Ames, and Oak Ridge has part of it. So this has been going on for like a decade. Now, after a little bit of that, in 2012, the US started mining again, minimally. But it was still not financially competitive. And eventually, in 2016, the last US mine was put on care and maintenance. Since then, some attempts have been made. And in 2018, there was a bid done, but look at the trend. Look at where China's production is and the monopoly that it has on resources. So how did we end up here? As I mentioned, the toxicity of the processes allowed China to do this much more cheaply than the US. So the separation is a challenge and the green process is a challenge. So remember this as we keep going through the talk, because this is what connects all of our efforts. So let me give you just one example. We said cell phones use REEs. In the late 90s, there were very few cell phones. Today you have 7 billion. Perhaps that was the 2018 figure, maybe now even more, right? And we need REEs for all of this. Computers, gadgets, tech, all has increased the same way. So the need for REEs that we had in the early 90s is very different from the need that we have today. And China is providing the demand. So this clearly has a strong national impact. Here I listed a few of the perhaps most important congressional and other resources reports. You're welcome to ask me about this. I'm not going to go into detail. There's a lot in here. Most of the time it has not pushed things very far until very recently that we have an increase in interest. There was an executive order at the end of September addressing this exact problem on our reliance and dependence on REEs and critical materials on foreign adversaries, particularly China. That's why this executive order came out. A month before that, DOE had invested 20 million for research on REEs. And although since 2010, this has been an important topic that DOE has supported, it decayed a little bit. Like in the last few years, you would have some more trouble finding funding for this. Look at it now, a 20 million investment, like straight out. So let's take a look at the reserves. We saw a map earlier showing us where all of this is in the world. Well, let's look at just an overall amount. China really just has 38% of REEs. The rest of the world has the rest. So the rest of the world has more. Now, disclaimer here, the type of REE and the mixture of REE you find across the earth is a bit different because it's geologically dependent, right? But the point here is like China does not have the most resources. It just has the cheapest way to separate them. So this creates a national security risk because we need these elements for our everyday life and defense particularly, and we have one dominant producer. Then if you have a decision on restricting exports from that producer, now we have a national security problem. And the mining production takes many years to even begin. If your mines are closed, if your separation industry is inactive, and your experts have not continued to be trained in radiochemistry to do this, you're not going to be able to start this tomorrow by yourself in the US, right? And I know this is something nuclear engineers tend to know a lot about, radiochemists being a shortage, right? That you have some from several decades ago and not very many now. So this ties in the same way with the expertise you need to separate REEs. So they're difficult, we said, but specifically separating contiguous ones, the neighbors. Because the REEs behave so similarly, when you try to separate contiguous ones, you have more trouble because they behave very similarly. That means if you put an extracting agent in a certain process to separate the neighbors, they will likely both like the extracting agent and come out together, or not like it at all, and none of them comes out, right? To affect this and to be selective, throughout the decades that we've known separations, we found solvents that are good at affecting the thermochemistry that occurs to give us the separation, but they are toxic for the environment. So we have challenges in demand for technology. We said batteries, magnets drive all our tech and defense. It's expected that consumer and defense application demand of tech and REs will increase rapidly over the next decade. Look at when we looked at the map from the 90s until now, how it climbed enormously. Medical applications that include lasers, MRIs will also increase. They're also being used, some of the actinides are being used for radiotherapy. And I know you're very well aware of these techniques. You've even had several great speakers on this last semester. So what is the solution? Well, we really need to optimize the separation. If we can optimize the separation, the US can start mining again and be competitive. But to optimize the separation, we have to design agents in processes that are greener. So with this, we can find alternative critical materials as well as we study the behavior of the chemical environment. So this is why we care about REEs. And we also are trying to recycle them. You may have heard recent efforts on coal ash and getting REEs from coal ash, or recycling old cell phones and extracting materials. That is not a simple and inexpensive process. But if we have a shortage, we're going to have to explore those avenues as well. So I'm not going to talk a lot about the uses of actinides. I think this audience is much more of an expert on nuclear applications than I am. But just to make sure we're all talking about the same classification, the actinides is just the name we give to the chemical elements in the row of actinium through lawrencium, which is normally represented below the lanthanides. Okay, so now we know why we care about actinides and REEs. So our target is radiochemical separations, optimizing the separations. And I said we're trying to use HPC. So let me try to talk to you a bit about the tools and where we are in being able to use HPC for this. So high performance computing, we refer to the machines and their supercomputers. This is a chart that was just released yesterday that Jack Donguera presented at SC. And this shows us the top 100 supercomputers as they have been evolving since the 90s until now. So feel free to ask me questions about this, but the one thing I want to focus on is the orange at the top, which is N1. That is the #1 supercomputer per year. And that one is the one that has achieved what we call a certain type of performance. So if you look in the mid to late 90s, we reached the teraflop era by one of the machines at Sandia National Lab. In 2008, we got Roadrunner at Los Alamos, and that's where we enter the petaflop era. And now we are entering the exaflop era. Now, we're developing things, and I'll show you some of the DOE investments in this in a minute. China says that they're going to get to exascale 2020, 2021. The US says 2021, 2022. I guess we shall see. And one neat fact here, the very first supercomputer, and I'm sure you know this, was dedicated, it was created and dedicated to nuclear applications at Los Alamos. Now notice it had 1,000 processors, 1,000. So I'm sure you've seen this many times as the HPC tree, as it's called, where we show the share of HPC in the world. The volume or the area represented by each part is proportional to the capacity of the supercomputer. You see here barely like 4 quadrants, not perfectly even, but you can see that 3/4 of the HPC resources in the world correspond to the US, Japan, and China. The rest of the world is over here. And we don't need a lot of details from this, but I want to point out a couple things. One is China has 42% of the systems, US has 22%, Japan has 7%. But in terms of performance, this is not just size, this is how well they can perform. US has 27% of the highest performing supercomputers, Japan has 24%, and China has 23%. in number of systems, China has the most, right? China has 209 systems, the US 110, Japan 33. But when we talk about share of performance, although China has the most machines, the US has the highest performing, 32 of the highest performing top 50. So that's important. So where are we with HPC, and why did I mention exascale computing? DOE has invested a lot of resources onto achieving a capable exascale era. And they have addressed this by integrating application development, software technology, hardware technology, and exascale systems. The idea is to really integrate applications, development, hardware, architecture, along with the workforce development to be able to take advantage of exascale. And if you look at how supercomputers have evolved, if we look at 2012, we had Titan. I'm sure perhaps many of you have used it. And now we have Summit that has been very famous at pushing out climate data and recently COVID results. For exascale, these three machines, Frontier, Aurora, and El Capitan, are an invested of $1.8 billion. And this is, it's not that the $1.8 billion goes only to the hardware. It covers other items, but we're talking about here building these machines, and I'll get to software in a second. So we've had, as we've seen, great advances in hardware. During the last decade, research investment has been great for hardware. Unfortunately, it has gone overwhelmingly towards hardware and not software. And this high need in software development and hardware-software integration is important for exascale, it's important for any application in science. But specifically, it's important for radiochemical separations because we fall very short in what we can do there. This is not just modeling of lanthanides, modeling of actinides, modeling of materials. We can get by there, okay, but the type of modeling we need to do to optimize separations falls very short in how the hardware-software integration can form. And I'll give you some examples. So we talked about REEs and actinides and the usage and why they matter to us. We also talked about current availability in HPC resources and where we're going in exascale. We mentioned the DOE exascale project. We also talk about an ecosystem out of balance. That is when we have great advances in hardware, but software is not following. And we talk about the dependence on foreign sources of REEs largely from China and why we have challenges in separating them at home and the toxicity implications and radiochemical separations. Now, these topics hopefully start to look more together to you by now, but they tend to be very separate. Radiochemists, HPC scientists, geologists are normally not together working on a problem. What we're trying to do about it is connect HPC, where we need to go with development to address specifically the separation and purification of these elements. So that takes us to our last bubble, which is, okay, so what are we doing specifically in the separations with what we have available currently with HPC and where we're going next with what we don't have? So here's where our lives get interesting with cost, accuracy, and HPC readiness, which software we have, where we can cut corners or not. I am not going to talk a lot about methods and electronic structure theory. I'll be happy to if anyone wants to cover details with that, but I want to mention a couple of things. When we talk about optimizing separations computationally, we need to describe a physical system. Basically, an element, let's say, is that in the middle, that is captured throughout a process to be separated from a mix, okay? So we really need to model the physical system and the reaction associated to form that, and I will show that in a second. And this is just very briefly to tell you why this is connected. This is just an example on a Californium compound I modeled a couple of years ago in collaboration with people in your department. So when we want to describe a physical system, we go to quantum mechanics in this case, and we represent our system, which is our wave function, as a function of the position of the electrons in the nuclei of the atoms in the system, right? I'm not gonna go into a lot of detail with this, but I want to point out that basically what happens here is we need to solve the equation. That's it. As you know, we can't solve the equation exactly for the Schrödinger equation for systems that have more than one electron, which is a problem there. So we start approximating the answer with various methods. So that's when we go to HPC, and we have scientific computing, computational modeling, data science. It's a whole array of methods and techniques and try to give an answer. When I say try to give an answer, it's because we have different ways to give an answer, right? We can go for extremely accurate predictions that will be amazing, but in some cases, not just limiting, makes it impossible to get an answer, versus can we compromise in some aspects and still give a qualitative answer that is relevant for separations. And remember this, it always matters which property you're trying to model, right? You often hear, you need at least, I hear this a lot, at least multi-reference, at least people name a method to represent the system. Ideally, obviously, we would like to have the very best method that you can find to represent a physical system, but you run short on your capability to model it computationally because the resources are not there. Now, sometimes you can still get qualitative representations. So let me show you this. We have available software that we can do many things with, but we have to compromise on the property at hand, finding the most optimum protocol to still give us an answer that can help move the separation optimization forward. And another challenge you have with modeling separations is like you're not modeling one compound. You know, sometimes you see a synthesis and characterization paper that has a beautiful new compound modeled with great theory, but it's one compound. When we look at separations, we're looking at hundreds of options at a time because we're looking at relative binding preferences. So we have to develop protocols for giving answers in this arena, in my point number one here. Now, what else can we do with HPC? Well, HPC in the exascale era is investing a lot in software. And there's software that is being redesigned, like NWChem is being redone to fit exascale and to take advantage of exascale. There's other codes, QMC-Pack, Madness, that will work great with exascale. QMC-Pack, for example, already functions really, really well, but they do not have the capability to model REEs or actinides at all yet. QMC-Pack depends on developing one variable, it's called pseudo-potentials, and they have not developed them. So we already developed them ourselves. And you know, we're moving forward. It's just very time consuming, but when we're done developing this, we will be able to use QMC-Pack in exascale machines to model separations. That will change the game. Madness also is not ready for REEs and actinides. And the reason I say they're not ready is because REEs and actinides, chemically speaking, on their electronic structure, they have orbitals that are the F orbitals that the rest of the elements don't have occupied. And that's what makes them be very different in the modeling arena. And the third item that I don't cover in this talk almost at all has to do with artificial intelligence, machine learning, any of these applications. The challenge for separation of REEs and actinides is that the data sets are not built yet. There's a lot you can do with AI and ML for actinides or for REEs even, just not for the separation part, because the thermochemical piece you need to address in the data set, they just haven't been addressed and there are not very many data sets. So we are creating them so then we can apply AI to them. So I'm going to show today a few examples of what we actually can do, because I guess this talk so far sounds like very gloomy. You know, we don't have the elements, we have a risk in national security. We're not ready to apply this for separations, but there are many things we still can do. So let me show you a model separation process. And many of you do this in your labs. So let's say we have a container. We're going to do a separation, either solvent extraction or an ion exchange. So we basically have an organic layer and an aqueous layer. The organic layer has your solvent and your extracting agent, that's HR. And the aqueous layer has a combination of the lanthanides or actinides to separate. Eventually, your lanthanide or actinides pushed is taken, picked up onto the organic layer, and is separated from the rest that were in the aqueous layer. In separations in which you don't have a solvent exchange, like a solvent extraction like this, you may have an ion exchange or an intermediate step. Those are in the interface, but those are details that we don't need for this. It's just overall the process can be described in this manner. This equation just says what I just said, just written in the chemical form. Same for the intermediate steps or ion exchanges. So let's look at some results. Ultimately, what we want from this, the reason we need the reaction and the reason why we need to model each one of these pieces every time is so we can calculate the Gibbs free energy of reaction. That result is what's going to tell us if the reaction is likely to happen, and most importantly, how much more likely is to bind onto one element versus the other. So here you have an example that we model. This were lanthanides separated with acetylacetone. And in red, you can see the experimental results. That's the minus log of beta 3. That's a partial constant, like the equation I just showed. And in blue, you see our predicted values. That was the relative Gibbs free energy amongst the reactions. So as you see, this is very good agreement. I wish I could tell you because we got this great result. Now we can apply this same protocol to everything and it's beautifully predicted. But that's what happens with lanthanides and actinides. The prediction is not the same. You have to be very careful on their orbitals, and this changes as we go. But the more protocols we apply, the closer we are to still predict binding selectivity today without the software enabling pieces that we're waiting for and developing. So let me show you a couple applications. I'm going to show you some results from an effort to separate lanthanum-140 from actinium-225 for radiotherapy, separating uranium, neptunium, plutonium, and americium for nuclear waste and other waste issues that we've encountered, and how we do some of the method performances to try to shortcut and provide availability of protocols for other groups in other areas. So let's take a look at actinium lanthanum for radiotherapy. I know you know this well. I'm just going to go quickly on why this matters. Actinium-225 is a multi-decay series alpha emitting radionuclide. It's been proposed for radiotherapy because it can treat cancer efficiently by delivering the energy onto smaller areas, which make the killing of the healthy cells much smaller than other treatments for cancer that we currently have. Unfortunately, we only have enough actinium-225 to treat approximately 100 patients per year. Actinium-225 is produced largely out of Oak Ridge. There's 2 other producers in the world, but even if you combine everything that they can all produce, it's about for 100 patients per year. There's also very few actinium-225 structures known. That's also because the material there's not enough material to treat people and to also do experimental research. So the limitation with the availability of material and the expert facility you need, you can't do this in universities, demands that HPC applications for this are going to give us the greatest advances on understanding the separation and purification of actinium. And why am I bringing this one up for separations? When actinium-225 is obtained from a thorium-232 target, you can get reasonable yields. But the challenge is that it does not come out radiochemically pure. One particular contaminant is lanthanum-140. Lanthanum-140 is very chemically similar to actinium-225, and that makes the separation very challenging. There have not been studies on separating actinium-225 and lanthanum-140 computationally or otherwise, really very much at all. We are working on this with Paul Benny and formerly with Rose Ball before she retired. And we've created some of the first approaches to even try to model this. And some of our results that we tried with carboxylic acids just to evaluate a commonly used extracting agent, we saw that, as you can see here, just to give you a snapshot, the green is the free energy of reaction of applying that extracting agent to lanthanum, and the purple is applied to actinium. And as you see the negative numbers go up, so it gets more negative as you go up. That's because it gets more stable, like it binds tighter. So what we saw here, that all the carboxylic acids bound tighter to lanthanum than actinium. And what we don't know is this gap enough for separation to be efficient? And in order to know that, we need to get some feedback from experimental results to see how this protocol that I developed here to model this is giving us an accurate representation of reality or not, and if we have to tighten some of our variables to do this. So as I mentioned, we need to benchmark this against experiment. This happens a lot when you start modeling systems that had not been modeling before. And we're also doing, in parallel to this, designing optimal ligands to deliver the actinium-225. Actinium-225, to be administered to a patient, has to be very well tightly encapsulated so it can be delivered to the zone that is needed and not attack other parts of the body. And we're developing the ligands to do that. And all of that is being done computationally. They can't do enough trial and error with this in the lab. So let me show you another example with separating uranium, neptunium, plutonium, and americium. The example we had here was for nuclear waste, and the ligands had been developed back when they were using dioxins, a type of chemical extracting agent or ligand for seawater. So in this case, we looked at electron withdrawing effects, thermochemistry, and binding preferences. We look at the relative characteristics. Electron withdrawing effects, for the purpose of this talk, I can tell you briefly, is just when something binds, one ligand binds to a metal or any other center, there's this exchange of electrons, right? We form these bonds, like somebody's withdrawing electrons, somebody's donating electrons. And then we look at the relative characteristics amongst the properties and amongst the compounds. So we looked at 6 compounds or 6 configurations that have the same type of ligand in a single form or in a double form. And we studied these six compounds for the 4 actinides I just mentioned: uranium, neptunium, plutonium, and americium. So we had a set of 24 compounds. See how very quickly you're looking at one property and suddenly you have a whole set of 24, and this is a very small set when we look at separations. Again, here I'm going to show you, and don't worry about the naming of the compounds, I'll show you the pictures. The higher the curve you see here, the more stable the compound, or more tightly bound. So here we have 4 curves: blue for plutonium, purple for uranium, orange for neptunium, and yellow for americium. And each one point, so let's look at all these points, correspond to this configuration for the 4 actinides. So what do we see here? Just from looking at this, and if you want to look at the paper, we have really great findings there. But I want to show you a couple of things that you look at when you do this HPC applications or modeling for separations, what you can see out of it. In this case, clearly the plutonium compounds are most stable in relative terms to the others. The americium ones are the least stable. And also the uranium and neptunium are very close together. And I'll tell you why that matters. Also, we saw that the compounds with double configurations were more stable than the single ones, which chemically is no surprise. So what do we see in this exchange of electrons? Well, we saw that plutonium was the one withdrawing the most electrons than the other elements in this particular set with this particular ligand. And we also saw that the ligand's donation was stronger towards the plutonium compounds. The donation was also stronger towards double compounds. And the backbone, one part of the ligand, was also more donating in the same way. Now, why am I pointing out electron withdrawing effects and donation and that curve from earlier? Those are different properties to calculate in different ways, and they're going hand in hand, showing us the same behavior. The reason to do that is useful is that getting the thermochemical piece computationally can be very challenging in accurate ways. Getting structural and electronic configuration withdrawing effects are much easier on the HPC resource side. So we can find correlations and find descriptions to optimize separations, not just from thermochemistry, which is not very common, but it's something we developed a few years ago, and it really works very well. So what can we say from this type of study? Well, we saw the plutonium compounds were most stable. The americium compounds were the least stable. We also saw uranium and neptunium have similar stability. We saw double compounds more stable than single compounds. We also saw the donation effects from the ligands were stronger than the nitrate groups, which are the little ones that bound in the single configuration, and the withdrawing effects as I just described. So how does this help us for separations? Well, given the configurations that we tested with ligands we proposed, we could say it's likely to be efficient to separate plutonyl from americial in this setting. And it will be likely inefficient to separate uranyl from neptunial. So see how, although somebody who might like very accurate methods will complain about the protocol, it's still qualitatively useful for separations. Now, if you wanted to do detection and you want to model a spectra, that is a very different story, and this will likely not be good enough. But for separations, that's why I keep highlighting, for separations, we can evaluate other properties and still move the field a bit forward. So one other, have 2 minutes. One other study I want to point out, and I think this could be probably the most useful for engineers. We did a methods evaluation. We studied nitrates specifically because they're used in separations all the time and they're present in nuclear waste, so they bind most often to the lanthanides and actinides in the mixture. We looked at the both complete series in gas phase and solution. These are parts of the protocol that we have to take in consideration: relativistic effects, the methods, the basis set, which are the linear combination of atomic orbitals we use for trying to give an answer for the Schrödinger representation, the multi-reference characteristics. All of this is beyond the scope of what I talk about here, but I just want you to know they are evaluated in case you are interested. This was the first time any study has been done like this. I still think till today, this is the only one that's been done throughout the actinide series. I'm giving you a quick snapshot. If you want, look at the paper here or ask me for it, and I'll be happy to send it to you. But I want to show you what you can see. So I'm going to have some names here that are kind of weird looking. There's no interest in you knowing exactly what they are for this purpose. I just want you to know this is something we use as a target method. It's still a single reference method, and you could tell me, well, you might need multi-reference. We can talk about that point. But the point here is this is a target method that is very expensive, and you cannot get it for the larger compounds. So what we evaluated were other methods with other base sets. Could they give me a similar description? So we tested out the entire series, and then we tested out the differences between the neighbors. Remember when I said it's hard to separate the neighbors? So here we get the free energy of formation for each reaction, for each actinide. And then here we took the difference, the thorium free energy minus the actinium free energy for the reactions, right? And that's what these little bars represent. So these dark bars here basically are telling us that is according to the target set for this particular study, that will be where we want to get. All right, so let's look at an example with uranium and neptunium. That will be the difference between the free energies for both reactions. So we use, these are basis sets for density functional theory calculations. This was a couple cluster calculation, and feel free to ask me the details about that. What you need to know here is that as I add colors, I am adding computational cost. I am adding a larger basis set. So what I want to show here is calculating things at this quadruple level makes some compounds impossible to calculate, especially for separations when we have so many. The others are cheaper. So look what happens here. We were looking at uranium, neptunium. Look at the target that is very expensive and limiting for large compounds, and look at what the other methods gave me. It's very close. This means that if you encounter a uranium-neptunium separation issue without other things that you need to consider, you could get by getting the binding difference with a cheaper method. However, as I said earlier, it's no one size fits all. If you do the same for strontium and fermium, not only doesn't give you a close gap to the target, it gives you an opposite reaction. It tells you one separates best than the other in different positions, and that is incorrect. So what does this tell us? We have to develop more targeted species for all of this. As I mentioned earlier, this was the first study done across the series for this. And I encourage you, if you're interested, to look at this paper. You're going to see little maps like this. There are hundreds of options. And that means if you want to model one of these, you could just look at the map in the paper and be like, oh yeah, I can get by with this, or no, I cannot get by with that, and I need better. So there's another paper that does the same thing for the lanthanides, and it's by Charlie Peterson. And it evaluates all these components that I mentioned earlier you need to account for. So with this, let me close and highlight what we're trying to do in the short term by developing protocols with what we currently have in HPC capability, what we're trying to do in the long term by developing software enabling capabilities to be able to use exascale and more user-friendly software for people to be able to do this a little bit more like out of the box, and highlight how the REs are critical for what we need, and that we need to focus on this, whether we're having an emergency from a national security perspective or not. Keep in mind the global resource and the dependence on China, and one neat aspects in this talk, I'm talking HPC and largest supercomputers. The components we need for the supercomputers also come from China, and they're making their supercomputers. So, you know, it starts to close in. Keep in mind the executive order and the recent funding from DOE, and also how separating continuous REs and actinides are difficult, how the separation process is toxic, and how we can make this greener and bring back production to the US, and how the DOE CP is having an integrative, holistic approach for the exascale era. And anyone who likes to develop software, please contact me. And with this, I hope I show you a bit how this interdisciplinary approach that normally you don't see, computational radiochemistry, we need for a lot of aspects. And, you know, within nuclear engineering, computer science, or other areas, it's really blending in together. I would like to thank funding and a lot of collaborators and computing time. And I would like to thank you for listening to me and inviting me today. And I'll be happy to take any questions.
Thank you, Deborah. Do we have questions? I have a general question. How widespread is the use of HPC for these types of separation processes? Who else in the United States is doing this kind of work?
Los Alamos does some, Oak Ridge does some. A lot, I would say, a lot of people use modeling in multiple capacities, and the HPC scale or small cluster at a university to model a compound or spectra. But for targeting separations directly, very few. Because it's just, the software is not user-friendly, and you run into complications that I didn't mention specifically here. You could tell me, you know, and I was hoping somebody maybe would ask me this, like, why don't you just use more cores, you know? Well, what happens with the software we have that we can use for separations, not for other things, but things we can use to model molecular compounds that we need for separations, you run into problems where, one, the ability the software has to use more cores is limited. So if you have a supercomputer with hundreds of thousands of cores, but your software can parallelize up to 7,000, doesn't matter that you have 100,000. It won't use it. And the second challenge is the memory allocation. A lot of the codes we use today were developed a while back. And they allocate memory to a physical node. So it doesn't matter how many nodes you have if you can only use the maximum memory on the one node, right? So you see how you hit walls way before what other people in other areas of science can use HPC to model. So that's why not a lot of people do it. And it's not, you know, it's a very tedious process. You can't just like submit a job and run it, and then you get a pretty picture out. It's very manual. And you also need a lot of chemical knowledge to model the reaction. It's not just modeling the compound for a spectra. You have to propose the reaction to model. That doesn't come from the software. So it's a lot of human design and HPC walls. Yeah.
Are there other questions?
Professor, I had a question.
Yes.
Yeah, so it's more like from another standpoint. So you explained the applications of these rare earth elements in like computers or say mobile phones. So there is a lot of e-waste. So is there any work going on regarding recycling of these REEs? Because we see these near critical and critical elements.
Mhm. Yes, there are a lot of efforts to recycle REs. You have even some local, there's some small business type companies that even address this. I can give you their info if you're interested. They are targeting that. The challenge is that it's just not cheap. You know, that's one of the biggest issues with separating REs is that to recycle them, you would have to, you know, get your phone and they will have to open it up and take the alloy that was used for some of the metals inside the phone and extract the RE from there, from the other things that were created in that material. So it's just not cheap. It's doable, but it's still cheaper to buy it from China. Yeah, but it is. Recycling could be a great opportunity.
Okay.
So I have one more question.
Mhm.
You can use these techniques to evaluate and model separations. Have you seen people use these techniques to try to evaluate and try to find compounds that you cannot separate?
Oh, it's the same. It's
I'm
the
thinking non-proliferation wise.
I don't know a lot of details usually on the non-proliferation side because I know some things are very protected, right? But
Yeah.
you can do the same. I can show you something here.
Just for an example, I mean, if we use fuel, and now the proliferation concern is that someone will get that fuel and they will separate it and get the plutonium out and
Yeah,
have a weapon. So,
right.
you know, could these tools bring additional value by finding out what could we bind this fuel with so that you can never separate it and you can never make a weapon with it? Have you seen papers on that? Have you seen people use these tools to do something like that?
I don't remember people talking about this specifically for non-proliferation, but I can tell you it's the exact same method. Because when I
Right,
tell
that's what I
you
thought.
you have, let's say you have this equation that will represent plutonium, right? And then you have the same equation for another element that is with plutonium. And you would not want them to be separated. So you're still going to calculate the free energy. And you're going to want, in this case, instead of wanting a large gap, so you could separate them, you will want a small gap in free energy between the two reactions. And the way you would drive that is because you're not changing the element. You have plutonium and you have uranium or whatever it is you have, right? But the way you change that is by affecting the environment or the ligand. So there's certain ligands that will bind to plutonium and the other element as strongly as the neighbor. You know, so you can use this exact same thing. I have been using it for years because I want to separate things in general and I'll keep them together, but it's the exact same reasoning. You will still try out the ligand and see if they have a large difference in binding strength. And in your case, you will want them to not have a large difference in binding strength.
So basically what you're saying is you could use the computational methods to find elements that you could mix into this fuel in some way so that it could never be separated?
Right.
Okay.
Right. And those will be when we call it ligands, right? The ligand is the one that will capture your element. You just want the ligand that will be as likely to capture plutonium and whatever other element you want to stay together with.
Okay. Do we have any other questions? Well, we're like almost exactly on time. So thank you, Deborah. I appreciate this. This ends the seminar today, and I hope everybody has a great day. Let's see. Okay, Dr. Habron says thanks too. Getting lots of thanks out there.
Oh, thank you.